Okay then, let's get going. So thanks for everyone for turning up to this session. It's always interesting to gauge the interest in Apache Cassandra. So is anyone here using it at the moment? In production? Just thinking about using it? Okay, so this is going to be quite an introductory talk. I'll start off talking about how I got into using Cassandra, because that should give you a really good idea of the types of applications that it's useful for. You know, if you've got your little shop and you've got 10, 20 users, you're probably not going to use Cassandra. It's very much geared towards running things at a much larger scale, and you need to make sure your use case fits that. Little introduction to myself. So I've worked with Cassandra for quite a few years now. Until very recently, I used to be building stuff with Cassandra. Over in the UK, I was building the internet television platform for the biggest television provider. You might have heard of Netflix. They're also one of the biggest Cassandra users, so really we just copied them. However, now I work for the company that kind of backs Cassandra. They push most of the code, they build products on top of it, so they actually give me time to come to conferences and talk to people about what Cassandra is. So you've really got to make sure, if you're going to use a distributed database, so that's the first fact actually, Cassandra is a highly scalable distributed database. Now you need to make sure that you need and should be using a distributed database. If your data set fits on a single server and you're quite happy that you'll have some downtime when that server is rebooted or patched or a tornado hits it, then Cassandra probably isn't for you. But we're going to talk about the use cases where you will want to use it. We'll have a little deep dive into how the internals of Cassandra work. So we'll see how it replicates data, we'll see how it distributes data across many different servers. We'll have a quick introduction to how you model your data differently, because it's not a free lunch. You don't get to use Cassandra and then you get to say, hey, I've got a scalable application. You really need to change the way in which you model data in Cassandra. And then I'll leave 5 or 10 minutes probably for questions. If I don't get to your question, just stick it on the app if you have it. And if you don't get me now, include your Twitter handle and I'll contact you later and answer your question, unless I don't know the answer. So it's time to get a little bit excited about databases again. First 3 or 4 years of my, no, longer than that. First 5 years of my career, I worked in organizations where we had a completely separate DBA team. There was even one company, they wouldn't even allow us to write SQL. You'd have to basically put in your requirements and they'd produce you a stored procedure. That's changed quite a bit, primarily because I moved companies. But in general now, when I work with a lot of companies, and the last company I worked at, there's a really big decision to be made, and the application development teams have actually been heavily involved in selecting a data store which is appropriate for their needs. And quite frankly, most of the time it is still a relational database. But for the exciting times it's not, then you've got a lot of learning to do. So it's time to get interested in databases again and to really understand the differences between the different databases. So 5 years ago or so, before I'd even heard of Apache Cassandra, I was looking at an application which looked a bit like this. This is the Tomcat logo for anyone who doesn't know, and this was a big Oracle database. This was the application, the very stupid architecture diagram for the system that was providing internet television in the UK. And it was the completely right design. It was kind of a proof of concept for, maybe 5,000 users. But it turned out that a lot of people liked watching Game of Thrones on their iPads. And people stopped liking being told when to watch television. Everything is becoming on demand and streaming, etc. There's quite a few seats at the front here. I won't be offended if you walk across and come and grab a seat. Now, we didn't suddenly flip to a system that was backed by a database by Cassandra overnight. So the existing system, got very cat-friendly. We essentially had to scale the existing, very traditional Tomcat servlet-based application many times with a big, expensive load balancer in front. And all the time, all of the data storage was done in an Oracle instance. So this bit might have been free, this bit was very expensive. What generally happened when we continued to do this is we'd eventually overload this component because Java services deployed to Tomcat with a load balancer in front, relatively easy to scale. Databases, not so much. So we like to kill this one quite frequently. The other thing that tended to happen, because this application that we were replacing had been built for a single server in mind, much like many of the databases we use today, we used a lot of this thing called session state. Now, session state is wonderful for developers. You know, user logs in, stick it in the session, it's in the memory of the container. Really simple, really easy to get going. Nothing wrong with that. However, as you come to scale applications, you realize it's actually quite a terrible idea. Because let's say we lose a couple of these Tomcat instances, the little cat sits on its head, everyone logs out, everyone goes back to the load balancer. Obviously, the sticky sessions don't work anymore because the server's gone, so it gets rerouted to a new server. So what happens? Well, either the Tomcats fall over, eventually, because like we were now talking maybe hundreds of thousands of concurrent users. So when one of the servers died, it was tens of thousands of users suddenly trying to log in again. So either that we killed the database or we killed the Tomcat, or a mixture of the two. So the kind of goal was to move to both an architecture on the application side of things. I'm doing a talk on Wednesday about that. But today we're going to talk about why we picked Cassandra on the database side of things and give an overview of how everything works. So our kind of plan was to move to, and we certainly didn't call it this, microservices at the time, but smaller separate components that we could scale, along with a database which you can continually add nodes to. And that should give you a good idea of when you might want to use Cassandra. It's when you're expecting your load to increase over time and you don't want to change technology, you just want to throw more servers at it. We didn't do this overnight. So we picked the two parts of the application which were killing the database the most. One was an audit log, so we're keeping track of everything a customer ever did. Log on, watch Batman, watch Game of Thrones, watch Game of Thrones again, watch Game of Thrones again, log out. And we made that a call out to another service which then used Cassandra. And this is the logo you'll often see. It's based from the Dynamo paper from Amazon, which shows a consistent hash ring. I'll explain how all that works. That's why you always see rings with Dynamo-based databases. And then by the time I left, we were starting to look a bit more like this. And I still see the system quite regularly because I now go in and consult for the company I used to work for. So scale was the main reason for us to move to a database like Cassandra. The second reason would be faults. So if you do not want to have downtime when servers fail, or you do your releases, or you're just patching the operating system, then you can't use a single server database. You know, so you're expecting faults and you want 100% uptime during those faults. So what do we mean by faults? So I've never had a tornado hit a data center yet, though my boss has. I've definitely had this one. So when I was working in Morgan Stanley and Hurricane Sandy hit New York, our data center was underwater for a week. We weren't using Cassandra, unfortunately, so we had a huge chunk of downtime. These are the things which cause the most outages and the most faults. Humans trying to upgrade and improve things. In general, they often do the opposite. And then there's the kind of run-of-the-mill faults which happen if you're running enough hardware. You know, hardware's going to fail, things like RAM. The network, especially, we were deploying this entire system into AWS. So you come accustomed to network faults. But the most important thing from my point of view as an application developer was we just like uptime when we throw away computers, when we do releases, etc. And if you've got a data store and a set of applications which don't run on a single server, then it's much easier to achieve zero downtime during deployment. That's enough fluff. Let's actually talk about how exactly Cassandra achieves this. So how do you actually, the first thing you've got to do is run a database across multiple servers if you want it to always be up or you want to scale it. Now, very traditionally, and virtually every database that's had this bolted on has had the concept of either primary, secondary, master, slave, means the same thing. If you haven't set this up before, what it essentially means is that you have a primary server that runs same as any existing, where you've run your data store. What it'll do, depending on the technology, is it will either asynchronously or synchronously replicate to other computers. Great. What does that give you? You get essentially a copy of your data on these two. And what the whole reason for doing this is if this guy goes down, then you can elect a new master. And this works really well for fault tolerance. It can also work really well for read performance, because what you can start to do is serve reads from the secondaries. Now, depending on whether you're using MySQL or Oracle or whichever technology, there'll be different configuration options for this. Most of them are asynchronous replication, though some do have synchronous replication. What that essentially means is when you send a write into your database, do we wait for these guys to respond before telling the user that the write is complete? Now, you probably think, why wouldn't you do that? Surely it's ludicrous not to. But the problem is if you wait for synchronous replication, then any kind of network fault in here, any of these guys falling behind, will affect your availability. And in general, you're going to move to distributed databases like Cassandra when availability is pretty important to you. The big advantage of this is essentially that, A, it's bolt-onable. Imagine you put your database developer hat on. Adding some functionality to replay writes to other servers, that seems pretty doable. Another advantage is you still typically, not guaranteed depending on the technology and choice, you're still probably going to get linearizable consistency in the primary. There's still a defined order of writes in the system. What are the disadvantages? Well, first off, this isn't going to work for scaling your writes. You've still only got one server. You need to get into sharding if you want to scale your writes with this type of system. So what is the alternative? And the alternative is essentially like a peer-to-peer, a masterless architecture, which when you first think about it is actually you think that's a terrible idea for a database. The database is normally that thing which allows us as application developers to be really lazy. The consistency is in this ball, this server I call my database. I don't have to worry about it. I can have primary key constraints. I can make sure I can have locks and make sure two people aren't updating the same field, etc. All of those features are great and allow developers to be lazy and to not really think about it. They're also the features that typically don't scale. And you remember at the start, we're talking about situations where we do want to scale. If you don't need scalability, look at other things. What are the disadvantages of this? So here what we're actually going to do is allow writes to go into any single server. So, customer Bob, he could be written to over on this node and this node at the same time. So if one of these nodes were to go down, we're fine, no downtime. You can update the record over here. The big disadvantage, of course, is consistency. You're very unlikely to get offered, that level of linearizable consistency that you would expect in a relational database. Okay? And before we go into the details of how that works in Cassandra's case, other databases do it differently, I just want to share with you a little story of eventual consistency in action. Because I work a lot with Cassandra now, I get asked a lot, hey, can I use that in a bank? I spent a number of years working in banks, and they're really some of the most hilarious uses of technology in the world. So we had traders on the left here. We had this system, we had Sybase in this example. Servers, we had some awesome transactions here. However, that wasn't quite fast enough, so we put a cache in there. Yeah, nice bit of eventual consistency in there. But it turned out this wasn't our source of truth in the bank. What we did, like most banks, is we had an IBM mainframe, and this was the real source of truth. And then because we enjoyed paying IBM lots of money, we also had their MQ series. So it was actually an asynchronous mechanism to take our transactions here, put them on a queue, and then put them in the mainframe. And there was a way of alerting if there were problems later. But most systems have a lot of eventual consistency if you don't realize it. If you're reading from read replicas in your existing database technology, that's also a type of eventual consistency. What Cassandra does is make you very aware of it and make you design around it inside your application. So let's see how that works. So Cassandra is heavily used now. I wouldn't say mainstream. I'd only really classify Oracle and MySQL and Postgres as mainstream, but it's used a lot. You very rarely go to a tech conference and no one's heard of Cassandra. It's heavily used by Apple. They're by far the biggest user. They have tens of thousands, even probably up to nearly 100,000 nodes of Cassandra in production. Heavily used if you listen to music, Spotify, again. Finance, lots of banks use it now. Rather than have their eventual consistency across multiple database systems, there are a lot of banks using Apache Cassandra. IoT, I hate that. It's a bit of a marketing buzz term. Not suggesting that you put Apache Cassandra on your Arduino, but most of these IoT-style applications are just producing vast quantities of time series data, normally immutable, and Cassandra is a great place to store that, and we'll see why. So it's based on 2 papers. It was originally developed at Facebook. One was Dynamo. We'll speak more about Dynamo than Bigtable. Dynamo is a paper that came out from Amazon, essentially for their basket service. We're going to talk about that in quite a lot of detail. Dynamo is actually a key value store. So Cassandra is based off the model of Google Bigtable, which is this wide row or columnar style storage of data, which if you don't know what that is, hopefully you will by the end of the talk. Kind of a differentiating factor of a Cassandra to a lot of other systems is that it's been built with multi-DC support, multiple data center support, from the very start. Every single node is aware of what data center it runs in. And that's really powerful when it comes to network partitions and fault tolerance, which we'll see down the line. The other thing is they don't have to be real data centers. You can lie to Cassandra. So another really good use case of the fact that each node in a Cassandra cluster knows which data center it's running in is the fact that you could just actually do some workload separation. So you can designate these nodes to face your customers, to face your customer-facing applications, and then you could have some other nodes and set up the asynchronous replication between them, and then run more batch analytical style jobs on that without affecting your customer-side performance. And that's really quite powerful, because virtually every company I've ever worked at, we regularly had to extract all of the data out of our database and give it to a wholly different team who would then put it in HDFS and run Hadoop MapReduce across it. So it's quite common to actually run both Hadoop MapReduce and Apache Spark directly on top of Cassandra nodes. If that's a topic that interests you, just grab me after and I can tell you how that works. So let's look into Dynamo, because most of the things in Cassandra and in most new technology in reality is between 10 and 50 years old. And most of the things in the Dynamo paper are describing things which are old. It's the fact that they were grouped together in a new way which actually makes it interesting. And these are the parts that we can talk about today. So we're going to talk about how we distribute data when we don't have a master. We're going to talk about consistent hashing. We're going to talk about how we do how Cassandra handles network partitions, and which pretty much impacts availability. There are some other sections which we won't cover in an hour's talk. It's a bit like gossip, which is a mechanism Cassandra uses for working out the members in the cluster, which stops becoming an easy problem when you're talking of hundreds, thousands of nodes across multiple data centers. Anti-entropy repair, that's something mentioned in the Dynamo paper, which is about if you've got that much data and it's spread across so many servers, they will slowly drift apart, and you need a mechanism for you keeping them together and repairing. Be it you had writes dropped because of network problems, entire nodes blowing up, hurricanes hitting data centers. There are a couple of parts that if you read the paper, and I do recommend you do, it's quite an approachable paper. It's talking about like a domain that we can all understand, which is a basket service running on a website. And basically Amazon discovered that if the basket service was down, they didn't make a great deal of money. So oddly enough, you have to put stuff in the basket for Amazon to make money. And they decided that eventual consistency is actually the right thing. They would rather you buy 2 things instead of 1, or 2 things instead of 3, than you buy nothing at all. And if this still happens today, this happened to me with a Kindle. I ended up buying 2 Kindles, and they just, I contacted them and they just fix it, which is the right model for their system. It might not be the right thing for your system. They were describing a key value store because it's, basket, blob. And if you do distributed key value stores, conflict resolution is really important. Why? Because, if you write the blob on either side of the world, when you come to merge them, the whole thing is conflicted. In Cassandra doesn't use vector clocks if you've come across them or you remember them from your computer science degree. It enables you to either model so you never have conflicts. This is we use the wide column data model. Or you can, if you want, use a more expensive operation called a lightweight transaction, where you can actually get linearizable consistency, but at the cost of availability. If too many of your nodes are down, those queries will start to fail. So the first part is about selecting the nodes that your data is going to be on. Now, I'm sure we've all done it, where we've accidentally slowed down production because we've run a rather large query on our relational database. You do it, you cancel it, you realize that doesn't cancel it, something slows down, and you really hope no one notices. That's bad on a single node. Imagine doing it on a 100-node database, and you try and do what's called a full table scan. Apple run 1,000-node plus Cassandra clusters, 1,000 servers acting as a single data store. And there's no way you can ever do a full table scan, or only if you're extremely patient. So Cassandra allows you to decide work out where your data is in a consistent fashion. And when we get to the data modeling section, that's going to be the motivation behind denormalization. Because you cannot spread your data for a particular query that, say, backs your website across hundreds of nodes. It's never going to give you a performance system. So how does that work? So imagine we had some data, with some regular kind of tabular data. It's a bit more like a map of maps. So we've got, first key Jim, second key age, 36. What Cassandra does and what other consistent hashing systems do. They take a particular part. We call that the partition key. It's hashed with an algorithm like murmur3 is the current default, but it's also pluggable. And that gives you a number. Now, murmur3 is a very large number. It's either 64 or 128 bits. Now, for example, I'm going to pretend that it really is between 0 and 1,000, so the numbers are easier for me to say. So we can pretend that Jim hashes to 350, Carol hashes to 998, etc. Now, the next secret part, well, it's not really secret, is that each node owns a range of this hash ring. That's why you often see the ring. Now, in reality, each node can own lots of little ranges, but while explaining this, let's assume that each node in a Cassandra cluster owns a single range of that 0 to 1,000. So we can visualize this like this. So we can say that node B owns everything from 249 all the way back to 0, which obviously leads us to be able to work out exactly where our data is. So if Johnny is stored, because Johnny hashes to 50, he's going to be on node A. Right? And every single node in the Cassandra cluster can work this out. So you can go to any node and request any data, and it's just going to coordinate your request. But it's obviously drivers can work this out too. So drivers actually are doing this algorithm as well and going directly to the node. But data does move in Cassandra because you add more nodes and the hash ring changes. So if you happen to go to the wrong node, don't worry, it'll get coordinated and be directed to the correct nodes. Now, if I were to stop there and say that's Cassandra, just a distributed hash table, it's pretty easy, right? It's not going to be a particularly great database. Because if you're going to spread, if you want fault tolerance and you want to be able to handle hardware failure, what would happen if node A goes down? You restart it, you upgrade your Cassandra version, a hard drive dies, whatever reason. Poor old Johnny is going to vanish, all right? We're going to lose it. That's a terrible database. Why would you want to use that? So the next part is replication. But before I dive onto replication, has anyone got any questions? No? I'll plod on then. Oh, yes, one question.
You said that you can talk to any node.
Correct.
So every node has this hash ring.
Mm-hmm.
So how do they get that?
So constantly in the background, a Cassandra cluster is using a gossip protocol where each node is chatting to 3 nodes and telling it what it thinks its current state is. So it's obviously the state of a distributed system at any particular time is next to impossible to know, but each node is constantly keeping up to date with nodes being added to the cluster and nodes been removed. What the nodes then do is actually basically push this information to clients as well. So it's not like a poll operation. It's a nice two-way protocol between a driver and a Cassandra node. And when a new node goes to the cluster, the nodes tell the drivers, so the drivers can update their view of this ring. Any more before we move on? Nope. So next is replication. Now, replication is important for a number of reasons. So we want to be able to handle hardware failure, but we also don't want a single point where we have to go to either read or write our data. Otherwise, if we had a hotspot, then we'd be back at that single server problem. And there are 2 types of replication in Cassandra. There's the simple way, the way that you should never use apart from on your laptop. Why? Because you don't really want to tell Cassandra what the data center or rack is of your laptop. So by default, you can easily spin it up and it'll be the simple replication. What this means is you just give it a number, between 1 and n. Very, very common one is 3. And Cassandra will replicate the data that many times. And the way it selects the replicas is it does the hashing algorithm, and then it will go to the next, n-1 nodes. So they're just going to be adjacent to each other in that ring. Now, there's a number of reasons why this is not a good idea. Well, imagine all those nodes end up being in the same rack in your data center. Or even worse, let's say you're running on some kind of cloud environment, either AWS or CloudStack on top of your own tin. What happens if all of these nodes end up on the same physical host? Again, Pretty terrible idea. So the one we're typically going to use is what's called network topology. Now, if you want to be tolerant to any level of partition faults, you need to be topology aware. And that's because where do partitions in networks typically happen? Well, obviously between data centers. Oddly enough, crossing the Atlantic is harder than, talking to a node sitting next to you. Between racks is obviously going to be probably one of the next most likely scenarios. The least is probably nodes sitting on the same LAN, right? Nodes sitting on the same rack. So what the network topology does, you tell every node in your Cassandra cluster which rack it's on and which data center. And again, you can lie, you can make this up. But what you're trying to do is give Cassandra enough information so that it's going to keep a copy of your data on different racks and in different data centers. So if you're AWS aware, Amazon Web Services aware, they separate their machinery, where you can put your virtual machines, into regions like US West, US East, EU West in Ireland, and then a very new one in Germany, I believe. So you could treat that as a data center, even though we know that Amazon actually have many data centers in that area. Amazon also have the concept of availability zones. So these are things which have different ISPs, they have different power supplies. So within Ireland, there's 3 of them, so that if an ISP goes down or there's a massive power cut, and they're going to put their availability zones with different providers for each of these. So they tend to actually be data centers, but you could tell Cassandra that they're racks, and that's actually the default behavior inside AWS. And what that means is, let's say we are running in EU West, and we wanted 3 replicas of our data. What Cassandra will do is, for each thing that you store there, it's going to put a copy on each availability zone. So Amazon would actually have to lose all 3 availability zones for you to lose any availability or to lose any data. Because you've got a full copy of your data inside each of your rack or availability zone, you can handle the communication, periodically going down, and Cassandra will catch up when the network link is restored. But it also means you have to be quite careful about how you deploy Cassandra. We as developers actually need to start getting involved in this. Okay, we need to make sure that we're not, say, putting Cassandra on a bunch of virtual machines which actually all reside in the same host, which happens quite a lot. Once we know how we need to replicate the data, I kind of like looking at a visualization of how it works. So I've got this fictitious example here. Now we're pretending we've got 2 data centers. So this could be 2 data centers in Europe, or because for fault tolerance, or this one could be in the US and this one could be in the EU because data locality with customers. What your clients do now, the driver in a distributed system, in a distributed database, is vastly more complex than your regular driver, which is typically maybe speaking to 1 or 2 nodes, maybe doing a bit of serialization, managing a few connections. The Cassandra drivers could potentially be managing many hundred concurrent queries to many thousands of servers. Okay, so there's quite a bit more little tweaks you can do in this guy to describe how you want your queries to be routed. The most important thing you want to do is make sure that your applications talk to Cassandra nodes in the same data center. You don't want to jump across, the Atlantic every time, because that's going to add a huge amount of latency. And this is pretty much the default behavior, how everyone sets it up. So your client in data center 1, it can select a coordinator. Now by default, that will be a coordinator which actually owns your data. There are reasons why you might not want that, maybe due to hotspots, etc. You can also base it off the latency that each node is responding to you, things like that. The next thing you decide, and this is per query, but you can set up defaults, you decide the consistency. So again, this is going along the theme where you as application developers, if you want to build systems that are spread across many data centers and handle hardware failure, you've got to think about it a bit more, and Cassandra makes you work harder. So the first thing it's going to make you do is decide a consistency of every single query. Now what does consistency mean in this? So let's just describe consistency level 1. That essentially means I want 1 node, 1 replica, to acknowledge this write before I go on my merry way, and I say that's complete. And we'll explain the other consistencies later. This guy, who we'll call a coordinator, can then actually respond because he owns that data. So yep, we've got it to 1 node. Asynchronously, in the background, what happens is this coordinator uses the algorithm, and this is deterministic, to decide who the other replicas are, and it sends it to them. and it does it to its nodes in the local data center. For all of your remote data centers, Cassandra makes the assumption that the network link is either slower or more expensive, so it's only going to copy it to one node in the other data center. It's then that node's responsibility to then, complete the replication over there. And at that point, you have a fully replicated piece of data. And we could have actually selected a different replication factor in each of these data centers. You don't have to replicate every table to every data center. I'm sure you can think of some examples that involve certain American government agencies where you wouldn't want to replicate it to certain of your data center. But that is the big key difference between other traditional relational databases and things like Cassandra. You have to be aware that if you do consistency level 1, and you immediately do a read, you might actually read it from this node, and you might get an old value. But you can twist these knobs, and you can decide basically how much latency, how long do you want to wait before that write's complete. And I just want to stop before we go about tunable consistency, and just make sure no one thinks there are any masters or any special nodes in Cassandra. The coordinator just does that single request. If that request fails, the driver will just select another one to use. The node in which we hash to is just one of the replicas. The algorithm deterministically selects the other replicas, either the simple way or the network topology way, and the drivers will happily just use the other two if the node which it hashed to was down. And as nodes are added to the cluster and nodes are removed, the rings just rebalance, data shuffled around. There's no special nodes. You can happily go around and knock off servers, etc. And if you're aware, if you've set up the network topology one, you can do crazy things like you can turn off 2 entire racks and know that there's a full copy of your data on the other rack. If you don't use network topology, then you're not sure, so you wouldn't just turn off 2 full racks. So consistency, that's the big, scary thing when you're working with a database like this rather than your traditional relational database. So the first thing you get to decide, now we spoke about consistency level 1 previously, but what happens if you wanted to wait longer? What happens if you wanted to read your own writes? You wanted that form of consistency. Well, you could write to all, but that's generally a bad idea. As soon as you write to all, you're actually going to have a bit of downtime whenever there's a node down, because there's no way a coordinator can write to all if some nodes are down. So we just forget this one ever exists. Okay, I shouldn't have put it on the slide. We never use all. What we might want to do, though, is read and write at quorum. What this means is that if we've got, say, 6 replicas, like in the previous example, 3 in each data center, we would get it to a majority of them, which is 4 out of 6. That means that if we were to read and write at quorum, we're always going to have one common node, so we're always going to get the data that we just wrote. However, that involves possibly an expensive network hop tower at the data center. So Cassandra also has a bunch of consistency levels called local. And that essentially means that you same equation, but you only consider the nodes local to your data center, and you only talk to those ones. So we had 3 local replicas, so we'd write to at least, or we'd get acknowledgements from at least 2, and then we'd check with at least 2 during a read. So we're not incurring that expensive hop across the Atlantic or whichever ocean it happens to be. A lot of people just trust Cassandra and just fire it in at 1. If you've got a write-heavy workload, then often people just continue to write at 1 and just accept the fact that when they read, they may get a slightly out-of-date answer. What they're doing there is trading off latency with consistency. Any questions on consistency before we move on? It's not a concept you'll normally play around with in your traditional kind of relational database. Yeah.
I have one quick question on performance.
Yeah.
How do you increase this factor, replication factor, influence on performance of all of application? And the time that the application should wait for that knowledge that such node as saved in few nodes.
Yeah. So correct me if I'm wrong, but the basic question is, how does replication factor affect performance? Because when you do reads and writes, you're going to have to communicate with more nodes. And it absolutely does. So nearly everyone in the world uses 3. So they can get, you want an odd number for quorums. Very few people will ever use greater, some people do use 5. If you're using quorum-based consistencies, then yes, increasing your replication factor is going to increase your latency, because you're going to have to talk to more nodes to achieve the query. But there are very few people who don't use 3, and most people use either 1 or quorum or local quorum, depending on whether they want to read their own writes. Any more questions before we move on? I have one other special type of consistency that Cassandra can do. Because one thing you might notice here if you're a consistency nut is that none of these, even if you did all, are going like write it all and read it all, are going to give you linearizable consistency. Because you can read a value, you can make a decision, then you can write a value, and in the meantime someone could have jumped in there and modified it. There is no kind of like lock you can do in Cassandra like you wouldn't be able to like begin transaction, end transaction, etc. However, lots of people complained about this because they chose Cassandra because, yeah, I need the write performance, I need the scalability, I need the fault tolerance, but why are you making me run an entirely different database just so I can have that one style query where I want to make sure that I have a defined order? An example might be, let's say you're selling cinema tickets and you've got 300 spaces. You could read Cassandra, how many have been sold? 299. Okay, I'll sell you it, and then I'll write in to say 300 at the sold. Now, 2 different servers could have decided to do that at the same time, and you've just sold 301 tickets. Now, actually, most airlines, etc., just happily do that. They overbook flights. But if you didn't want to do that because you're a nice company that didn't want to annoy your customers, then Cassandra has another level of consistency called lightweight transactions. Now, what that does is, let's say we've got 3 replicas. Then to decide the next value for a particular field, it will actually run a round of Paxos and actually decide on the next value, and everyone else trying to write it concurrently will get a failure and say, someone else is writing it, and it gives you the value that that is attempting to be written. Now, that's great. But if you happen to, jump on the Cassandra bandwagon and use that feature for all of your reads and writes, you've probably selected the wrong database. Because that needs a quorum of nodes to be up, and it gets slower when it's contended. Because obviously, like, lots of people are trying to propose a next value, and they have to agree and come back, and then you have to decide whether to retry. So that adds quite a bit of overhead. It is, 30 to 40% slower than just writing normally into Cassandra. But it means that if you have that one use case, perhaps unique usernames, that you don't need to run a second database just to do that. So the next thing I was going to talk about is basically how Cassandra scales, because hopefully I've barked on sufficiently that the way in which Cassandra replicates data is deterministic, so anyone can work it out. Hash, follow the ring round in simple, or hash, follow the ring until you find new racks, if it's the network topology net one. But this isn't going to remain consistent if you add new nodes. The ring is going to change. So how does that work? Because, if you can't add new nodes, then it would be a pretty terrible database. You'd have to deploy 100 nodes for when your website was doing 100 writes a second. So how does that work? So, well, first you need some computers. Yeah, you tell the computers where to go. Just give it a few nodes in the Cassandra cluster. They will communicate with them, and they will say, "Hey, I would love to join your cluster, please." And the cluster says, "Why not?" Those nodes actually don't own a full segment. They own lots of little segments. And some of those little segments are given to the new nodes. This can be time consuming. If you've got 10 terabytes on every single Cassandra node, we obviously need to stream quite a lot of data. So while this is happening, the default way you're going to do it is that those new nodes are not going to service requests until they've been fully bootstrapped, is the term. And once they have had all the data streamed across, then they join the cluster. Existing clients that are connected into other nodes, they get notified about the new servers, and then you're all happy. The data which the new nodes have taken over, that isn't deleted from old nodes until you tell it to as an operator. Now this can, of course, be automated, but you're going to say, yep, that node's fine, clean up and delete the data, you don't need it anymore. It's not going to service requests, but it is going to keep a copy of the data. And this is just because a lot of times when the servers fail, when you first put them there, they often fail right at the start or 10 years later. So that it's quite common for new nodes, nothing to do with Cassandra, just computers, to fail when you first add them to a cluster, because you've maybe bought it fresh out the rack and then suddenly you're piping 20,000 writes a second to it. And you've decided that maybe the hard drive is a bit faulty. So it's just an extra safety step so the data isn't removed. So the next is data modeling. So this is going to change a lot. The language that you're going to use to interact with Cassandra is called CQL, not SQL, and it is very similar to SQL. So it's going to make you feel like, yeah, I know what I'm doing here. But what you basically need to do is forget everything that you've ever learned about data modeling and third normal form, etc. Because whereas these techniques are fantastic for when the data is on a single server and you want to be able to do ad hoc queries, that type of data modeling is a terrible thing to do if you've got a data set size which is going to be spread across tens, maybe hundreds of computers. So what do you need to do? Well, unsurprisingly, you need to denormalize it so that all the data that you need to query for a particular function in your application will live on a single Cassandra node. And when I got into Cassandra, that was pretty scary. I've been doing this stuff for a long time, and suddenly someone tells me I need to change the way I do it. One technique, which I think is a great way to learn how to do this, if you can find a small child and you can ask them to model your data, they'll do a really good job. All right? They're just going to say, what does your web page, how do you need it? That's how I'm going to store it. That's about as much as you need to think about it. There is more things you need to think about, but you definitely want to throw away all of that idea of not duplicating. You want to be able to put all of that data nicely on a node so your client can go directly to a single node. This gives us the great characteristic that if we've got a 3-node Cassandra cluster and we model that data and we denormalize it, assuming we're, say, reading and writing at consistency level 1, what we get to do is go to a single node, get the data back. We then go to a 1,000-node cluster because we're Apple, and then the actual thing which a driver needs to do to get your data or to write your data hasn't changed. It goes to a single node and it gets the answer back, and that's because you've denormalized. If you do try and normalize your data in Cassandra and do things like Cassandra doesn't support joins, but if you just say, nah, I'm going to do that inside my application, these things tend to work when you have really small Cassandra clusters. But as soon as you have a Cassandra cluster which spans many nodes and you end up communicating with all of them, then that type of query is just going to get slower and slower and slower and slower until the point you're going to denormalize. Much like we often do in relational databases as well when we begin to shard. Once you've accepted that, as I said, the language is really easy. It's called CQL, which sounds a lot like SQL. It's not by any means one of the SQL standards, it just looks familiar. There are many things in CQL you would never do in SQL, like have collections and things like maps and sets. I think things that you'd never, because you're going to store one-to-one and one-to-many relationships inside the same table in Cassandra. But the tables kind of look the same. The really important bit is this primary key, which we're going to spend a little bit of time on. Inserting, very similar. Selecting again. The big difference is this where clause. Cassandra is going to limit you a lot. You're going to hate Cassandra when you first get into it because you're going to be like, why can't I do that? And what it basically tries to do is stop you from doing anything that wouldn't be able to be satisfied by a single server. You can add an extra bit on here called allow filtering, which will say you can then do things which shouldn't work, but you don't want to do that in production. If you've got allow filtering on here, it basically means you can go to many nodes in your Cassandra cluster, and it's a really bad idea. The next thing you're going to do is remove anything. You're going to forget that things like auto increment ever existed. Now think if you were building a distributed database, you had a new job, you went and worked for DataStax, and someone said to you, could you just implement auto increment? And we obviously need these values to be unique, and 1,000 servers will be requesting it. Okay? How do you decide what the next value is across tens, hundreds, even a few servers? That kind of thing does not scale. It's called a global invariant, and you don't want global invariants in distributed systems. So you're going to use a lot of things called UUIDs. This is not a Cassandra thing. UUIDs will be in any type of distributed system that you use. But essentially it means that you're not going to get these lovely IDs for your data like 1, 2, 3, 4, 5. You're going to get these lovely 128-bit values. You're also going to have funky things like your own types inside the database. I mean, how exciting is that? You're going to be able to create them. Anytime you think, I might want to do a join between these two entities, think your own type embedded inside your table. Now, Cassandra has collections like sets and lists and maps. So if you had a user which had multiple email addresses, you wouldn't have another table, you would have a set of email addresses. Or if you wanted to give them an identifier, you would have a map of email addresses. Yeah?
Does this list is how you understand the normalization?
Pardon?
Is that the concept of denormalization you mentioned?
Yeah.
Is that expressed by those sets and lists in the single table?
Yeah, so the question was, are things like sets and lists and these types the way you kind of do denormalization or understand denormalization? Absolutely. I think these didn't used to exist. So you used to have really big tables with lots and lots of columns, which made developers feel really uneasy about doing this. As soon as we started having collections, which was Cassandra 2 maybe a year or so ago, and user-defined types, which was Cassandra 2.1 about 9 months ago, it really makes developers feel good about denormalizing. Better, I will say. Any more questions where we go? So there's one really important part of Cassandra that I have not yet mentioned. And if you've come across it and you've looked at those tables of what on earth a database is, you've probably come across the term columnar store, wide row store, and there's nothing I've said so far is kind of like explaining what that is. Now, many years ago, you used to be exposed directly to the on-disk format that Cassandra uses, and it is a wide row. It means that you get to pick as a developer how the data is ordered on disk. Why do you want to do this? So that you can do really quick range queries across vast quantities of data. Single disk seek, sequential read. And the way you're exposed to it in modern Cassandra and CQL is by selecting an appropriate primary key. And how you select the primary key is going to dictate exactly how you can query it. If you need to query it two very different ways, then you will store it two different ways. So this is another example Cassandra table. It's raw weather data. It's from a real application. We have a weather station ID. The assumption is that we're going to be collecting data from many tens of thousands, maybe hundreds or millions of weather stations. Our primary key is made up of year, month, day, and hour, which means that we're basically going to store one weather event for each weather station per hour, because that's our uniqueness constraint. And at the moment, we're only storing temperature, but in reality, this table included lots and lots and lots of different figures from a weather station. So what's important here? So let's pull it out. So a primary key is made up of two parts. The first part is the partition key. And you can put as many columns as you want in here. What's really important when you're thinking about how you're going to query the data, they all need to have the same partition key. Why? Because that means it ends up on the same node. It means you're going to get really quick queries. That's the kind of dynamo part of Cassandra, because that's how Cassandra distributes data. So we're assuming with this data model that we're going to query things just for a single weather station ID. If we wanted to, say, query for all weather station IDs in a state or a country, we would be changing our partition key. And it might be that we would store it in multiple ways so we can query it efficiently in multiple ways. The next part of the primary key, apart from giving us uniqueness, gives us on-disk ordering. So every single type in Cassandra has a natural ordering. You know, obviously numbers are easy, characters, lexicographical, and these ones were all integers. And if we go back to this table, the default is ascending. So it's going to be ordered, you know, when the dinosaurs were around all the way up till now. Now, often with things like these types of data models, the data that you're going to query the most is the most recent data. So you can just flip these around. So this is basically saying that we want to do it descending rather than ascending. So this is the partition key, these are the clustering columns. This is how we control the wide row format. This is how we are able to query many rows that we see in a CQL table in one go and be guaranteed that they're going to be ordered on disk together. So when we select a primary key, that gives us the node. So the first thing stored on disk is going to be the primary key. And after that, all of the things in the clustering column are going to be used to order the data. So if you, assuming you can see this, we can see that the temperatures are stored by, you know, they're all for the same date, so the 1st of the 12th, 2005, but they're stored for the hour 10, followed by 9, followed by 8, followed by 7. So regardless of how big this data set size was, we'd always be able to query the top of it really efficiently. It's going to be going right to the start of the partition and getting a really, you know, say we could do limit queries on this, We wouldn't even need to use the clustering columns in our queries. We'd just say where the station ID equals, you know, London, UK, limit 5, and we get the last 5 temperatures. If we wanted to do date ranges, then we can start to say, oh, when the time is less than 9 but greater than 7. And to visualize this, you know, doesn't matter what size the cluster is, weather station ID is going to tell us exactly which node to go to. This is the cool bit, right? So this is one of these range queries. This is where you can get some really awesome performance out of Cassandra because it is very sympathetic to how disks work. And even SSDs are much quicker at sequential I/O than, you know, random I/O. So because we've decided the order, when we do queries like this between 7 and 10, then we can go directly to the start, and then we're reading like this. You're not exposed to this when it comes too much back into your application now, because what it does is it gives you it back as if they're multiple rows. Okay, so think no different, say, from JDBC, from relational database. That's the programming model, but you just have to select a primary key really carefully to make your queries efficient. And, you know, programmers typically like this, right? We don't have to change the way we program, but we do need to change the way we data model. And that's pretty much it. If you've got more questions, we can, you know, grab me afterward. Just to kind of summarize, though, Cassandra has a particular use case, right? It is when you want to run at a certain scale, or you've got a particular, you know, love of availability. Now, some people say, don't you always love availability? But that's not always the case. There are many domains where you can turn the application off, you know, at 5 p.m. when the trading day stops, you know, so you don't need downtime for patching operating systems and deploying software. But if you need 100% uptime, Cassandra is a really good choice for the database. Or if you're a real optimist and you're expecting, hey, my data set size might be 10 gigs today, but I'm expecting it to be vastly greater in the future, Cassandra is a really good use case there as well. So yeah, it's all about availability. If you love the CAP theorem, very much Cassandra is focused at AP, and you know it's always going to pick availability over consistency, unless you use lightweight transaction, which is where you're kind of flipping Cassandra around. As a developer, the only thing you really need to learn is how to model differently. There are some, like, when you get into really high performance data models, you play around with the size of partitions and things to make it more efficient. But in general, that's the biggest mindset change. Most people, when they get into Cassandra, they try to create a table for their entities and bad things happen. Okay, so what you really want to do is just right from the upfront, you want to get into that mindset of I only want to go to a single server regardless of my cluster size. It used to be a real pain to program with. When I started programming with Cassandra, it was a horrible thing. It was like HBase, if you've ever used HBase. It exposed that on-disk format. You're exposed directly to that map of maps, and you had to construct the inner map. You know, so you had to start putting bits of your data inside, you know, column keys and things like that. It took a while to learn. Once you learned it was okay, but it certainly wasn't intuitive if you come from a traditional background. The time you'll fall in love with Cassandra is when you have your first big hardware outages or power outage. One of my first ones where we actually deployed a Cassandra cluster with the completely wrong file system, and it wasn't performing particularly well. So a rack at a time, we could just take the nodes down, delete all the data, you know, put the correct file system on, and then boot it back up. There's a command you can run in Cassandra to say repair, and it copies the data back over to those nodes, move on to the next rack. I mean, that's just amazing. Like, I was just like, wow. I fell in love ever since. But I'm always hesitant, and I'm always warning developers that if Postgres is going to work, use Postgres. So on that note, if you've got any questions now, happy to answer. You can get me on Twitter. I blog a lot about Cassandra, and there's lots of free training on here. DataStax have recently just made all of their training for free. If you Google DataStax Academy, that's for Apache Cassandra and the products that they build on top of Apache Cassandra. So on that note, I will call it done and take any questions. Yeah. Sorry, could you speak up a second?
Do you need practically to keep range IDs to work in Cassandra for queries?
Sorry, I didn't understand the question. I'll come clear.
You have a range IDs, correct? As a part of the key.
Yeah, you have your partition key. So that would be something typically in your data model. That decides the partitioning. The range is the clustering columns, yeah.
Okay, but do you keep it practically in applications? Do you need to worry about the ranges, that partition keys?
So the size of partitions, how many things have the same partition?
Do you need to keep partition, for example, to know which node you need to request, or you just keep it?
I get the question. So do you as an application developer have to even worry about the partitioning to work out where the data is? And the answer is no, Cassandra will do it for you. The thing you have to worry about is the cardinal, like the number of things which map to a single partition. If you've got 5 customers and you make your partition key customer ID, you're only ever going to be spread across 5 nodes. So you need to make it granular enough. But because you can put multiple columns in, you could put customer and day, and then suddenly you'd use lots and lots of servers. Yeah.
Does Cassandra support multiple inequality conditions?
So the question was, does Cassandra support like multiple things to query by or indexes? So you always include the partition key. If you know, because that's why you're using Cassandra, you want to go to a single node. Anything in the clustering column you can use from the left. So because it's how it's ordered on disk, you can use this one and then this one and this one, but you can't skip one out, if that makes sense. Cassandra has secondary indexes, so you can index additional fields. However, think how secondary indexes would work in a distributed system, right? You're going to do a reverse index lookup, you know, from like the field which wasn't part of your primary key onto a partition. And then potentially you then might have to go to every node in your cluster depending on how it mapped. So you can use Cassandra secondary indexes so you can query by other fields, but in general that's just a convenience. You're going to get the best performance by duplicating the data and storing it twice with different partition and clustering columns. Any more? Okay, thanks very much for listening.